Okay, welcome to the Xeto deep dive. And in this video, we're going to take a look at using some of the command line tools in Haxall to work with Xeto. Also cover the syntax and then actually work with some Haystack data and how we combine specs and Haystack data to do validation. So in this video, we're going to be working with Haxall. In this particular video, I'm using Haxall 318. This is an open source version of the Haystack tools that we use, and it's got the reference implementation of Xeto. Hopefully there'll be future implementations. And Haxall has is basically two command line tools we're going to look at today. So one is the Xeto command line tool, and also the Haxall command line tool. So Xeto is a simple tool to work with libraries, take a library, generate it to JSON, whereas the Haxall tool is more an interactive shell. Haxall is the functional programming language that is included in Haxall for working with Haystack data. We've integrated working with Xeto specs into that language too. So it's a great interactive tool. All of this can be run from the command line. So just to note that the Haxall runtime does use the Java virtual machine. There's a prototype of this that runs with Node.js that you can reach out to and talk to us about. But these are all command line tools. So even if you're a C# shop or some other technology, you should be able to interact all of these tools through the command line and just standard in, standard out is the idea here. So let's take a look at first the Xeto tool, which is in your bin Xeto. It's a bash script or a batch file, which you can run. And it's kind of like Git. It's got some subcommands here. The one that we're going to look at first is this environment command. So when we run the environment command, it's going to list the libraries we have installed. So sys is sort of your core language library with your basic language types. It's kind of like the java.lang of Xeto. We can see a bunch of PH libraries that we've got installed, and then we've got some examples from ASHRAE Guideline 36, which specifies best practices for air handlers and VAVs. Now, these are just the libraries that ship with this particular version of Haxall. This will change over time, obviously. And you can see in the Haxall design, all of your libraries are going to go into a directory called libxeto. They're going to be the name of the library, which is a dotted name, and then they're going to have this file extension, xetolib, which is really just a zip of the source directory is how that works today. So let's say we want to create a new library. We have a command line that'll stub that out for you. It's called a init. And we can see that basically it's sort of got one option here, which is the qualified name of your library. So library names are dotted names. The beginning of the name should be either a domain you own or an organizational name you've registered with xeto.dev. For the purposes here, we're not going to follow best practices. We're just going to give it a short name, which is HC for Haystack Connect. And let's go ahead and do that. And let's call HC here. And we're going to see that it's going to stub out some files. So in the Haxall design, the source of your Xeto always will go under source Xeto, and then the directory based on your library name. You always got a lib.xeto, which is your metadata for your library, instructions for the compiler. And then it's also going to stub out just a dummy file for specs.xeto. And you could change that later. So we'll go ahead and accept these. Now, at this point, if I run Xeto environment, we're going to see that HC now shows up as a library. We'll also see that it's using the source. So whereas these other libraries are coming from libxeto, the fact that we have the source code here means that every time we use this library, it's actually going to compile from the source directory. There is a tool, which is bin xeto build, which will build this, basically a build. It'll compile it, make sure the syntax is all correct, and it will actually generate a libxeto file in the lib directory here. Okay, it's really just a zip of the source that we've validated compiles correctly. Okay, so we've got this library. Let's go ahead and take a look at it. So I'm going to jump over to VS Code, and so start from scratch here. So you can see it generated these files. a lib.xeto and a specs.xeto. And I've got this extension installed, the Xeto extension. This is a really nice extension you can install into VS Code that will give you color coding, autocomplete, syntax checking, etc. Let's go ahead and I'm using that extension so we can see how it all works. So we got these two files here generated. So specs.xeto has just generated a dummy spec. We're going to look at that syntax in a little bit more detail. And it generated this file. So this file always has to be in every library. It's always got the same sort of boilerplate template. It's always going to start with pragma, which is basically means instructions to the compiler. It's always going to be a library type. And then everything between the angle brackets is your library metadata. So a spec, a library is itself a spec, right? And its metadata is the library metadata, and then it contains the specs, which are the children of that library. The doc string, this is basically your some summary of your library here. Your version is always going to be a 3-digit SEM version. The major version is needs to be rolled every time you make a breaking change. You've got your dependencies. These are the other libraries we're going to depend on, and there's a whole little syntax about which versions you depend on. And then organizational information, which is, I would say, still a little bit in design right now. Okay, so now that we've got this library, let's actually take a look at exploring it, and we're going to switch over to the Axon tool now. So I'm going to go run Axon. And it works similar to other sort of dynamic programming languages like Python or Ruby. You can pass an expression on the command line. You can actually put a little shebang in a text file and run it as an Axon script. And it's got an interactive version, which we're going to use. So we'll go ahead and enter the Axon shell. And you can type help to get some help. Just note that in Haxall, we do strip the documentation to keep the download very small. So if you do want to reference function documentation, you do need to look at haxall.io where that documentation is all available. So the using function basically tells us what spec libraries we've got imported into our shell here. And we're going to start off with just sys. So for example, I could type string and I could see he's a spec that subtypes from scalar. He's got some metadata here between the angle brackets. But I don't have my spec loaded yet, okay? That's because I need to import the HC library into my system. I'm actually going to import every library I have installed using star. And you're going to see it's going to load all those libraries we found in our libxeto directory, including HC now, which we're loading from the source directory. So now if I type my spec, you can see that he's getting printed out, okay? My spec is convenience for basically printing him, and we're going to see there's some options here. For example, I can add a documentation string. We're going to see later that one of the options you'll use a lot is effective. So here we're just printing the declared metadata and slots, whereas effective is going to take into account all of the inherited metadata and slots. Okay, so let's go back to our source code. And let's just explore the syntax here. So we got this doc string here, okay? It's just // can be multi-line. That's basically going to go into your metadata as a tag called doc. And then you've got your spec name, type that you're deriving from, okay? In this case, it's dictionary. Then if you want metadata, you could put some angle brackets here. And this is basically itself just a dictionary. You could have marker tags, name value pairs. And then everything between the curly braces is what we call your slots. Most of the time your slots are a field or a tag that's required. It could be optional. And then we also have other slot types like queries that we're going to look at the end here. So let's just create a single slot here, and I'm going to call it A. And it's a spec too, so it's got a name. It's got a type. In this case, let's call it number. I could put some metadata in here. And then I can give it a value. Okay. Now, in the case of scalars, instead of curly braces, we have basically a string encoding of that scalar. Okay. Let's go ahead and go back to our shell. Now, of course, if I print this, I haven't I haven't changed anything. The shell only works with what it last loaded into memory. If you want to reload, it's explicit, and that's a function called data environment reload. Okay, and as a matter of fact, I'm going to use that so often, I'm going to assign that to a variable so I can just do this. And now that I've reloaded that and I go back and I print my spec, I can sort of see how it got compiled. Okay, and when I'm printing it, it's a pretty print of what that spec looks like, and you can see basically it looks exactly like the source code here. My names have sort of become qualified names, which we'll talk about. These basically library : and then spec name. Okay, so it's basically spec : type, angle brackets, metadata, curly braces, slots. That's sort of the format. The grammar is very simple if you look at it. Basically, all of the sophistication is in the type system, not necessarily the language itself. Okay, so last thing we're going to look at here is I'm looking here as a pretty print. The other thing that you may want to do is look at this from the AST perspective. So AST is a term we often talk about when we're talking about programming languages, compilers, parsers. It stands for abstract syntax tree. It is basically just the data structure that represents the Xeto files themselves. So in this case, I can use spec AST, my spec. Okay, it'll actually return the AST as a nested tree of Haystack dicks. Most of the time, you can actually pipe that to print JSON. Typically, is how you'd look at this. Okay, so if we want to see how does the AST look in JSON, every spec is an object. The fields of that JSON object are the metadata with a few special tags. Base is your base type that you derive from. There you can see your doc string went in there. It's just a piece of metadata. That foo tag we added. And then slots are all my slots in here. And you can see that they just mirror that spec. They've got a type, a min, val, val, etc. Everything that got compiled just basically gets turned into a tree of JSON objects. Okay, so we'll look at that in a couple other examples too, because it's a different way to look at really what your specs look like under the covers. Okay, so now that we've sort of covered the basics, let's do a little bit of deeper dive into the syntax for scalars and the syntax for collections. So I'm going to go back here and let's just get rid of this for example. So you can see here that I've got a name, a type, and then my scalars are basically always in string encoding. So if we look at, for example, JSON, right? JSON has a couple scalars. It's got quoted strings, it's got numbers, it's got the keywords true and false for Booleans, and it's got null. Okay, and then your collection types, we have lists in square brackets and objects in curly braces. In Xeto, we really just have scalars and collection types. Scalars are always quoted strings, and collections are always curly braces. And that's because we have explicit types. So instead of using special syntax, we always annotate things explicitly with types. And that's how we infer what the values are. Now, I said everything's a quoted string, but there's actually some syntax sugar for that. And that is if your string is a number, and it contains some special characters, you can just omit the strings. So these two things are identical. It's actually a personal preference whether you quote it or not. By convention, we leave the quotes off if you don't need them. But if we actually compile this and look at it, we can see that those things came out exactly the same. Okay, the fact that I quoted it or not was really just a matter of choice. Now, let's say we leave the type off, okay? So if I said 1, 2, 3 here, or even I said 1, 2, 3, that type basically is going to be just default to a string, okay? Let's just look at that so we can see what that looks like. And you can see that both C and D came in as a string. And this is an important concept to understand because we're not going to infer that just because that string was a number, that it's a number. It always has to be explicitly typed. Now, one of the things you will see is that oftentimes your types are inferred from your base type. So even though we may be leaving a type off, that doesn't mean it's not explicitly typed. It's just being explicitly typed by the compiler through your type hierarchy. Okay, but in this case, since we're not inheriting from anything we don't know, we're just going to default those to strings. Okay. Now, of course, Haystack is built around the idea of markers. We can create markers too, like this. We just basically give it a type marker. However, as convenience, you can just leave the marker off. So as long as this spec is lowercase, we'll infer it to be a marker. Let's reload that and see what that looks like. And you can see that foo and bar basically come in as markers. Okay, so in a pretty print, we'll leave it off. If we look at this from an AST perspective, you can see that these slots are basically still just typed as sys : marker. So the other really cool thing we have, of course, Xeto is an open-ended type system, is you can create your own scalar types. So the example I always use is creating a color type. And you basically just create a named spec. You subtype from scalar. You can give it a metadata. You can give it a default value. We'll do that. And let's just add a red here. Okay. And we can give this actually a regex if we wanted to force a pattern on this that the compiler will check. And let's reload that and look at that. And we can see now that this is our new scalar type, which is HC : color. So completely open-ended for you to create your own scalar values. And really a scalar value is basically just a typed string encoding, right? In the end, everything has to be encoded to some sort of string encoding. And then if you may or may not need quotes depending on what that string encoding is. All right, so that's scalars. Now we're going to move to our collection types, which are always in curly braces. We've been looking at dicts here, right? So let's go back and just simplify this and start over. Start off with a very simple dict with a couple fields. Okay, so subtyping from dict, I've got 3 fields here, A, B, and C. And this is exactly like sort of a class type in Java or a record type in a lot of languages. And we're basically just saying this is an object that has these 3 fixed fields. Okay, I'm leaving the type off here, so they're going to be implied to be string. Just compile that and look at that. So it's basically what you'd call a record type. Okay. Now, giving a name to the slots is optional. Okay, so I can come up here and I can actually leave the name : off. Okay, but everything's still a dictionary with keys. So what happens in this case is the compiler will generate some keys for me. Okay, and that algorithm is always _0, _1, _2. So let's just recompile this, look at it. Now in the pretty print, you're just going to see we're leaving those names off. If I actually look at this from an AST perspective, you're going to see that they are still basically named slots. It's just we gave them an auto-generated name. Okay. So we typically will use this in 2 circumstances: lists, and typically a lot of time in our point templates, we don't give a name to all of our points, where they're just unnamed specs, and the compiler will generate _1, _2, _3, etc. So if we go back here, let's take a look at lists. So a list, like in JSON, you'd indicate that with square brackets. Now in Xeto, everything's just curly braces, and we do it through the type system. So we basically just type it as a list. It's still curly braces, and we let all of our children be auto-named. And they actually have to be auto-named. And when we run that again, we'll see basically looks a lot like a dictionary, except that it's a list now because of the type system. Okay. Now the last thing I want to show you here on the basic collection types is that the parameterization. So in Java we call these generics, and a lot of languages we call them parameterized types. And that's the notion that a lot of times with collections, I want to fix the type of what is inside that collection, whether it's a list or a dictionary or custom collections. And you do that in most programming languages like this. If we want to say this list only contains strings, right? We typically use curly braces. Some languages like Scala might use square brackets. But in Xeto, everything between those angle brackets is actually tags. So the only thing we do here is we actually give that type a name, which is of. Okay, so this is how we would do a parameterized list type in Xeto. Okay, we'll just compile that and see how it works. And you can see basically that just becomes, another tag in the meta. But it's an important tag because that's what the type system can use to make sure that, oh, this is a list of strings. If you try to put something in that list that's not a string, you get a compile time error. Okay, not all those checks are actually in place at the moment. So this sort of leads to the next question, which is, what's happening with these names? So here you notice I'm always using simple names. I'm using list. I'm using string, okay? But really, this is a library name, a qualified name, and I can do it like this, okay? But how is the list getting turned in string getting turned into sys : list and sys : string, okay? And this is basically name resolution. The compiler does this for us. And a lot of programming languages do this. We use the simple name in our programs. And then there's always a mechanism to resolve those simple names to their fully qualified names. So for in Java, we do it with the import statement. And in Xeto, we do it through the depends. So the names that I use in here, okay, are always going to be resolved against the names found in these libraries I depend in. Okay, so for example, in the PH library, okay, I have a type called equip. Okay, so PH equip, this is the standard spec for all Project Haystack equips. And if I wanted to create my own equip and subtype from it, right, I could come up here and I could say, I don't know, let's call this my equip. And I want a subtype from equip. Okay. Now, if I try to compile this, you're going to see I get an error, unresolved type equip. Okay. That's because I haven't told the compiler where to find that simple name equip, okay? I have to tell it in my dependencies. So I can come over here, and I'm just going to copy this guy and paste him in, and I'm going to change this to PH. So now I'm depending on sys and PH. You always have to depend on sys, by the way. Now that all the names from PH will be available to me to use in my specs. So now if I recompile this, we can see that worked. And if I look at my equipment, you can see now he is subtyping from PH : equipment. Okay? So that's how our name resolution works. And it's nice because in our programs we use these simple readable names, but under the covers, right, everything has these very explicit qualified names, which gives us our global namespace so that we can reuse tens of thousands of specs and not worry about name collisions. So the last thing I just want to look at here is there are times where you may have the same spec name from multiple libraries. In that case, you do actually have to use the qualified name. We may in the future add some sort of import as some languages have. If we want to see how that would look, like I'm just going to come in here and I'll create something called equip. Okay, so now I've got an equip from Project Haystack. I have an equip from my HC library. If I was to reload this and try to resolve the simple name equip, I'm going to get an error like this. Ambiguous types for equip, I've got actually the simple name maps to these two qualified names, Project Haystack equip and Haystack Connect equip. So that's a case where you need to basically then use the qualified name. Okay, so let's go ahead and fix this and just make sure we're compiling again. Okay, and now we see equip is going to map to Project Haystack equip. Okay, so that sort of talks about the name resolution. So next topic is composition. We've definitely already seen the primary redo composition, and that's through inheritance. So in some cases, many of the popular languages, mainstream languages, Java, C#, TypeScript, etc., are object-oriented languages, and they have this notion of inheritance. Xeto has that notion of inheritance, and inheritance basically means I'm going to inherit all the metadata and all the slots from my parent type. Okay, and to look at that, let's actually start off with a new example. I'm going to say my equipment is a dictionary that has the equip tag. Okay, and I'm going to say my meter is going to subtype from my equip and has the meter tag. And I'm going to say my electric meter is going to subtype from my meter with the elect tag. Okay, so this would be typical inheritance. This actually maps exactly to what you see in the Project Haystack spec taxonomy, which we just took our conjuncts and turned them into camel case specs. So this guy's basically going to inherit from this guy, which means the meter tag's required. He's going to inherit from my equipment, which means the equip tag's required. So let's go ahead and compile that, and let's look at my electric meter. Okay. Now default, if you remember, the print function only prints your declared slots. So the only thing declared in my electric meter was the elect tag. But if we print with the effective option, okay, we can see that the effective version of this spec is that you have to have all three of these tags. Okay, you have to have the meter, the equip tag, the meter tag, and the elect tag. Okay, and this is what inheritance is doing for us. The same thing would happen with our metadata if we had metadata in here. Okay, so that's the primary mechanism of composition. Now, we have the notion of compound inheritance through two types, the AND types and the OR types. They correspond into TypeScript, what you'd call in intersection and union types. We don't use those terms because they're a little confusing when you talk about how the slots are inherited. So for example, in TypeScript, in intersection type is, from a set theory, is the intersection of two types. But from the slot perspective, it's the union of all of the slots from your inherited type. So we use the terms AND and OR, but it's the same syntax as TypeScript. So let's say I decide on some of my assets I want to capture the serial number and the install date. Okay, so I'm going to create a my asset spec here, and I'm going to say serial number is of type string, and I'm going to say install date is of type date. Okay, and I say I want all my electric meters to have that information, so I just merge, okay, my meter and my asset together, and this is an AND type. So it's basically going to take all of the tags, slots from my meter, and all of the slots from my asset and merge them together. And if we look at that, and then we go ahead and print this guy again, you can see now that his effective slots are everything that he had before, plus now he has serial number and install date as required tags for that particular piece of equipment type. Okay, so that's an AND type. Now let's say sometimes serial number is actually just a number, okay? Sometimes it's a free-form string, but sometimes it's a number, and I want to allow either one of those. So that's where we use the OR type. And we just do that with a pipe symbol, just like you do in TypeScript. And this is basically saying serial number can be either one of these types. So if we go ahead and reload that and look at that, we can see that that's coming through as an OR type. We have multiple types too there. We have 3, 4, 5, etc. And the last thing I want to look at is a maybe type. Let's say serial number is required, but install date is optional. You may have it, you may not have it. But if you do have it, it needs to be of type date. And we do that with a maybe type, which we add by adding a question mark on the end of the type. Okay, and if I recompile that and take a look at it, you're going to see it's got this little question mark on the end of it. So before I leave this, those are your basic composition mechanisms: normal inheritance, AND types, OR types, maybe types. Let's look at it from the spec AST perspective. My electric meter. Okay, and let's look at how that works. So one of the things about Xeto is everything just has one base type. Okay, so if it's an AND type, the base type actually becomes sys : AND. And then if you want to look at what are the compound types of that AND, it goes in this tag called ofs. Okay, so of is how you parameterize a collection. Ofs, plural, is how you parameterize the compound types and OR. Okay, and if we come down here and look at the OR type, you can see it's the same thing. He subtypes from OR, and then he's got the ofs of the compound types. And then if you want to look at the maybe, maybe is just in the AST is just a marker basically in the metadata. In fact, actually, if we come over here, you can actually write this just like this. It means the same thing. Okay. Well, I got to spell it right. So run that, we run it again and run it, you'll see that basically exact same thing. either of those syntaxes will work. The question mark is just a little more concise. Okay, so that sort of brings us to the next topic. So here, everything we've been covering so far, I would say sort of syntax. How do you create and compose specs to build your type system? Okay, now we're actually going to look at how we use that type system. So one of the key aspects of Xeto is that it's a mix of what we call nominal typing and structural typing. And what these terms mean is nominal typing, which is by name, just means that two types are compatible only if they are explicitly inherent by name. Okay, so if you're a programmer, for example, Java, C++, C#, these are systems that have nominal type systems. Okay, and they work good, and we actually use those for scalars. Now, in languages like Go or TypeScript, we use what's called structural typing, which means I don't necessarily have a piece of data that's explicitly identified by a type. All that matters is it fits the shape of the type I'm trying to use. Okay, so it's sort of sometimes in dynamic languages you might use the term duck typing, but we use the term structural typing, and it basically just means a spec. It defines a shape of data, right? A set of slots that I have to have. We also see maybe a set of relationships I have to have, and then I either fit it or don't fit it. Okay, so in Haxall, we implement those two things with two different sets of functions. One is the is functions is our nominal checking, and the fits functions is our structural typing. Now in Xeto, we use nominal typing for scalars and structural typing for collection types, dictionaries mostly. Okay, and this works out well. So we don't want to infer a string to be a particular scalar type. You have to explicitly type it. Okay, but when we're working with Haystack data, I don't necessarily haven't annotated my dictionaries that they're fit this particular type, right? We just check that type through the fits functions. Let's take a look at how that all works. So first let's start off with the nominal typing, which is scalars. So for example, in the syscolon, we have an integer type, okay? He subtypes from number. If I was to look at number, he subtypes from scalar. If I was to look at the scalar, he subtypes from object, which is the root of the type system, okay? And this is sort of an explicitly named type hierarchy. So if I want to check these types, I use spec is. So I say, is spec a number? It is, okay, because it's explicitly in its hierarchy. Scalar is in its hierarchy, and object's in its hierarchy. Now, string is not in its hierarchy, so that would return false. So spec is basically checking two specs to see if they're nominally type compatible. Now, if I have instance data, right, so if I just have a hi there string, right, I can pipe that to the type of function, and it'll tell me what its type is. Okay, of course, it's a string. And I use the is function to check instance data. Okay, so spec is was checking two specs, whereas is takes a piece of instance data and says whether it matches a type. And in essence, is just this. Get the type of string. I need some. Oh, sorry. It's this. Is essentially saying get the type of string and then pass that the spec is to see if they're nominally typed. Okay. Now dictionaries are always going to come back as just dictionaries. So a dictionary will always fit dictionary. Obviously, it won't fit a scalar type like string. And this is where we get into the fits. Okay, so to start talking about structural typing and fits, I'm going to create a new little spec here. Let's just start over from scratch and create a myAHU, and it's going to just be a dictionary. And I'm going to say this spec requires that you've got a display string, the equipment tag, and the AHU tag. Okay, so it's basically I got these three required slots. Display has to be a string, equipment and AHU have to be markers. Let's reload that and just take a look at it. Okay, it's pretty much what we expect. So now let's actually create a dictionary here. So I'm going to create a dictionary that should match it. So this is AH2. He's got the AHU and the equipment tag. Okay, this would be a very simple entity for an air handler. He has a display string and he's got these two marker tags. Actually, this would be a mostly complete example if I had the site ref. And basically, if I was to say, do you fit are you explicitly in my AHU? Okay, it's false because I haven't in this dictionary said I'm explicitly my AHU. Okay, but from a shape perspective, I do fit my AHU because I have all of the required slots. And that's what the fits function does. Not futs, fits. And I say, yeah, that's true. You do fit me. Okay. Now, let's say I did something that seems not so good. Let's say display was a marker tag, right? That would be incorrect. And I would say, no, you don't. You do have the display tag, but it's of the wrong type. And so I'd say, well, why? Tell me why. Maybe I don't understand why I don't fit. And that's what fits explain does. Okay, fits explains takes one or more records of Haystack information, and it tries to fit them to a spec. And if it doesn't, it reports all of the errors back to you. Okay, the errors come back to you as a grid. Here I don't have an ID tag, so I just generated one. So let's actually try this with an empty dictionary so you can see what it looks like when you got multiple errors. He said, look, the dictionary you passed me had 3 errors. You're missing the required slot display, and we're missing these 2 required markers. Okay, so this becomes the basis for how we build up validation. Okay, we're looking at, in this case, we're looking at specific tags on a dictionary and deciding whether they're present or not, if they're required, and second of all, are they of the right type? Okay, now to really validate Haystack data, we need to validate the graph of data. Okay, so we need to bring relationships into these checks. Okay, and before we could talk about that, we need to talk about queries. So queries is a mechanism in Xeto basically to create named ways to traverse the Haystack graph. Okay, and in order to do this, we actually need to load up some data. So I'm going to go to the examples here. I'm going to use Charlie, which is the smallest example. I'm just going to copy this link address. And I can load that data up as my working set with the load function. Use backticks here because it's a URI. And now I've basically got that example data in memory I can work with. So I've got my site. We can see if I read all my equipment, I've got some VAVs and some air handlers and some, looks like some VFD meters. So I can start sort of playing with this data. So now I've got, in my working set, I've got some Haystack data. I've loaded up all my specs. I can start playing with these guys. So the first thing I'm going to do is I want to look at, let's read a space temperature. I don't have a space, it's not in zone. Let's read an air temperature. Okay, so so this is a filter, of course, and I've got, I matched this particular record. Okay, so this is VAV21 space temperature. Okay, this is what a point looks like in Haystack. We've got our equipment ref, we've got site ref, we've got some marker tags here that tell us it's an air temperature sensor. And so one of the things that we want to do is we want to be able to traverse these equipment refs, okay, both ways. Okay, so in Haystack, a point references its contained equipment through the equipment ref. Okay, and if we look at the point spec, okay, this is from the standard library. A point is anything that has the point marker tag, and then it's got this slot called equips. Okay, now equips isn't a tag definition; it's a query. Okay, we know that through the type system. And the way it says, it's basically saying if you want to get all of my parent or ancestor equips, okay, you do it by traversing one or more equipment refs. Okay, that's what the little plus sign means there. And it's got to basically, it's got to fit the equipment type, which itself is just anything that has the equipment tag. And with this query, it's sort of a declarative filter, if you will, that you can use by name now. Now in Haxall, we do this through the query and the query all functions. So if I go back and I look at the space temperature and I pipe that to query, okay, and then I give it that name of that query, which I do with point.equips. okay, and I query that, you can see it's going to find my parent equip, which of course the space temperature of VA21, his parent equip is VAV21. Okay. Now in Haystack, most of the time we're more interested in the other way. Given a piece of equipment, get all of your points. Okay. And if I was to take this guy, let's take this guy, read by ID. Didn't copy that right. Okay, this is our VAV. Let's say I want to go from here and get all of my contained points. Okay, so likewise, if we go back and we look at the point spec, he's got this equips query. If we look at the equip spec, he's got a query called points. Okay, and the way that you resolve this query, okay, is you just run the inverse of the point.equips. Okay, and find everything that fits a point. So if we use this query, let's go back to our VAV21. I'm going to do query all equip.points. That's my space temperature, sorry. Let's get my actual VAV. There's my VAV, and let's do query all equip.points. Okay, and we get all the points that are associated with that equipment. Now what's cool about this query is it'll actually handle nesting. So if you actually nested your equipment and had sub-equipment for ducts or fans or pumps or whatever it may be, this will actually traverse multiple levels of equipment ref for you. Okay, so this is a very powerful way in our specs to organize our relationships. Now, what's cool is this is open-ended, you can create your own. So let's say I wanted to create a query with just my temperature sensors for my VAVs. Okay, I can do that. Let's go back to my code here, and I'm going to create a new type called my VAV. I'm not going to subtype from anything, and I'm just going to sort of go back to the equips. Let's look at this. I'm just going to do something almost exactly similar. I'm going to copy this, paste it in my query here. I'm going to call this temp sensors. Don't need it to be qualified. I'm going to use the same inverse that we already have, except now I'm going to change this to temp sensor. Okay, and I'm going to create temp sensor as my own little spec here. And I'm going to say it's anything that has the temp, the sensor, and the point tags. Okay, so basically what I'm saying here is I've created a named query, and it's going to use the same inverse relationship we already said, which is going to follow equip refs back to me. But instead of finding just things that fit point, it's going to find things that fit this particular spec, which is you have to have these 3 tags. So let's reload this. Just make sure it looks good. Okay, and let's go back to that query I did. So here, equip.points finds all of my descendant points. But now I have my VAV, and I'm going to say temp sensors. And it's going to find just those 2 points within that set that have the temp and the sensor and the point tag. Okay, so this is relationships or queries. Okay, so now to bring it all together, right, and we talk about validation. We've already looked at how validation works with tags on your particular record. Now we need to start talking about validations with the graph, about your relationships, your contained relationships, your flow relationships, etc. And to do that, I'm going to look at the guideline 36 examples we have. So let's look at guideline 36, reheat VAV. And I'm going to use the effective and the doc options here. Okay, so these are all source code you can find on GitHub. And these are examples. Once again, guideline 36 is an ASHRAE standard, I guess you will, of best practices for control sequences and air handlers in VAVs. We use that as a good example see how you can model stuff with Xeto. So to meet the guideline 36 VAV spec, you have to have the equipment tag, you have to have the VAV tag, you have to have the hot water tag, you have to have the single duct tag. But what's more interesting here, what we don't talk about, is this. So the points query is actually inherited from equip.points, but you can see between curly braces we've added some other specs. Okay, these are come from the library ph.points, which you can also look at. And when we do this, we're creating what we call a constrained query. And we're saying, in order to fit this spec, you need to run this query, and you need to find exactly one of these. If you find multiple, it's ambiguous. That's an error. If you find 0 of them, that's an error too. If you want 1 or 0, you can actually put a little question mark on the end of these guys. Okay? So let's go back to our VAV. Let's make sure this is our VAV. Okay, so this is Charlie VAV 21. Let's see, do you fit guideline 36 reheat VAV? Okay, no. Well, let's ask why. Okay, so we got actually a whole bunch of errors. We got 7 errors. So first of all, we're missing some tags. Okay, I don't even know if these VAVs in this model are supposed to be reheat VAVs, but they're missing the hot water heating tag, and they're missing the single duct tag. Okay, they're also missing some required points. Okay, I've got my thing really zoomed in so you can't see everything, but they're missing these 4 points, and we also have an ambiguous match. So the zone air temperature set point, actually we had 2 points that matched that spec. Okay, and I could actually run this on, let's run this on all my VAVs. Okay, and I could basically get a grid of all of those errors. Now all these VAVs are the same, so they all have the same 7 errors. Now what's cool about this, right, is this is just itself a data structure. You could encode this to Zinc or JSON and export this into tools and reports, etc. But the goal here is sort of what we've been building up is all of these concepts, right? We start off with specs to basically check the tags on a particular dictionary. We had the notion of queries to model the relationships between your different dicts. And then we had constrained queries, and we bring it all together and we start to develop a complete validation system. Now, obviously we're not done, but you can see there's a tremendous amount of working code here that you can start playing with. But we sort of start off with the foundations, right? We've got the building blocks. You can put specs together, you can compose them. We start putting together, the ability to do validation, and then we can start building up from there as we get more complete solutions. Okay. So, anyways, this will all be in Haxall 3.18, at least as a first pass, and we'll be doing a lot more work in the coming months and the coming years.